Hi, I'm Michael Borenstein, and I'd like to welcome you to this workshop on meta-analysis. A couple of years ago, I was traveling with my wife and daughter in Italy, and we came to a town called Meta. I jumped out of the car to take this picture. What really caught my attention, though, is this next picture, which shows how to get to the center of town. I was struck by the fact that this picture captures the goals of a meta-analysis. One of the goals of a meta-analysis is trying to find the mean effect size. Another goal is to understand how the effect sizes in the various studies vary about the mean. This idea is reflected in this picture, where we see the mean effect size in the center, and we see how the effect sizes in the individual studies vary about that mean. But what's really interesting is this. What you're looking at so far is only the top half of the sign. This is the full sign. And I think that this is a reflection of the way that meta-analysis is often taught. It should be pretty simple to get to the center of town, but this sign makes it confusing. Meta-analysis is pretty simple when it's taught properly, but it's often taught in a way that makes it seem confusing. My goal is to explain meta-analysis clearly and simply. And by the way, when you actually get to the center of town, this is what you find. My hope is that you'll find this course to be rewarding as well. The material in this course is based in part on the text Introduction to Meta-Analysis that I co-wrote with Julian Higgins, Hannah Rothstein, and Larry Hedges. Those of you in the social sciences will probably recognize Larry's name. Those of you in medicine will probably recognize Julian's name. And those of you in organizational psychology may recognize Hannah's name. I should also mention that a lot of this work was funded by the National Institutes of Health in the United States and also the Department of Education. So let's get started. Rather than start at the beginning, I'm going to start at the end. I'm going to show you the results of a meta-analysis so that you can understand where we're going, and then I'll go back to the beginning and show you how to get there. This is a meta-analysis conducted by Cannon et al. It addresses the question, is a high dose of statins more effective than a standard dose in reducing the risk of a cardiovascular event? If you go to a physician and she recognizes that you have high cholesterol, she will often prescribe a statin. The statin lowers the level of cholesterol, and the hope is that it will reduce the risk of a cardiovascular event, such as a heart attack or stroke. Generally, the physician will start you off on a standard dose, such as 10 milligrams a day. But one might ask, if 10 milligrams works, then maybe 20 milligrams will work better. Researchers in 4 different hospitals had this same idea, and in each case, they conducted a randomized controlled trial to test the idea. The 4 trials followed essentially the same protocol. Patients who had high cholesterol levels were randomly assigned to either of 2 groups. Those in one group were assigned the standard dose, and those in the other group were assigned a higher dose. The researchers followed the patients over a period of time and kept track of what proportion of the patients in each group had a cardiovascular event. The results of each study are plotted here. For example, we can look at the PROVE-IT study. The risk ratio in this study is 0.84. This means that patients assigned to the high dose were only 84% as likely to suffer a cardiovascular event as compared to those on the standard dose. The risk ratio is what we call an effect size. An effect size is simply the index that we use to quantify the impact of the intervention. In this example, we're using the risk ratio as an effect size, but there are many other options to choose from. Depending on the kind of data reported, we might elect to use a difference in means between groups, or a correlation, or something else. I'll be using many different kinds of effect size indices over the duration of the workshop. While this particular example happens to use the risk ratio as the effect size, everything we discuss here applies also to any other effect size that we might use. In case you're not familiar with risk ratios, I'll offer a quick overview. A risk ratio of 1 would mean that the risk of an event was the same in both groups, and that would be indicated by this anchor over here. A risk ratio of less than 1 means that the risk is lower in the high-dose group, and a risk ratio greater than 1 means that the risk is higher in the high-dose group. In the present example, the risk ratio was 0.84, and this means that patients assigned to the high dose were only 84% as likely to have a cardiovascular event as compared with those in the standard dose. If we subtract 84% from 100%, we get 16%. And another way to say this is that the high dose reduced the risk of an event by 16%. In all 4 studies, the risk ratio is less than 1. So it's obvious that the high dose group did better than the standard dose in each study. In this study, the risk ratio was 0.84. In this study, the risk ratio was 0.86. In this study, the risk ratio is 0.80. In this study, the risk ratio is 0.89. Each study gives us the risk ratio for one population, the patients in a specific hospital. And the summary gives us the mean risk ratio across these hospitals. The mean effect size is a risk ratio of 0.85. Again, we can subtract 85% from 100% to get 15%. And this tells us that, on average, the high dose reduced the risk of an event by 15%. Now, let's go back and have another look at each study. For the first study, the effect size is 0.84, but this is bounded by a line that goes from 0.68 to 1.04. That line corresponds to the confidence interval, and let me explain what the confidence interval means. This is a study that was performed at a specific hospital, which worked with a particular population. The 4,162 patients in this study were sampled from all eligible patients in that population. For these 4,162 patients, the risk ratio was precisely 0.84. However, our interest is not in this particular set of 4,162 patients. Rather, we want to know the risk ratio in the full population. For example, there might be 100,000 people living near the hospital who have high cholesterol and could have been enrolled in that study. The risk ratio in our sample serves as an estimate of the risk ratio in that population, but it is only an estimate. The actual risk ratio in the population is almost certainly lower or higher than the risk ratio in our sample. So, when we report the risk ratio, we also report the confidence interval. This speaks to the precision of the estimate. In this case, the risk ratio in the sample was 0.84, but the risk ratio in the population could fall anywhere from 0.68 to 1.04. So, in the full population, it's possible that the high dose reduces the risk of an event by as much as 32%. Or at the other extreme, it's possible that the high dose actually increases the risk of an event by 4%. Now let's look at the second study. The risk ratio in the sample was 0.86, but the risk ratio in the population could fall anywhere from 0.72 to to 1.03. Now the third study. The risk ratio in the sample was 0.80, but the risk ratio in the population could fall anywhere from 0.70 to 0.92. And finally, the fourth study. The risk ratio in the sample was 0.89, but the risk ratio in the population could fall anywhere from 0.74 to 1.01. Consider what conclusions the researcher was able to reach in each of these studies. In the first study, it's possible that the high dose reduced the risk as compared with the standard dose. It's possible that it made no difference, and it's possible that it increased the risk. So, we cannot conclude that the high dose is better than the standard dose. In the second study, the confidence interval again includes 1, so we cannot conclude that the high dose is better than the standard dose. In the third study, the confidence interval excludes 1, so we can conclude that the high dose is better than the standard dose. And finally, in the fourth study, the confidence interval again includes 1, so we cannot conclude that the high dose is better than the standard dose. So, based on the confidence intervals, only 1 out of the 4 studies allows us to conclude that the high dose is better. Many people tend to focus on the p-value and whether or not the p-value is statistically significant. We can do that here as well. In the first study, the p-value is 0.106. This is not statistically significant, so we cannot conclude that the high dose is better than the standard dose. In the second study, the p-value is 0.097, and again, this is not statistically significant. In the third study, the p-value is 0.002. This is statistically significant. And finally, in the fourth study, the p-value is 0.069, and once again, this is not statistically significant. So, based on the p-values, only 1 out of the 4 studies provided evidence in favor of the high dose. Note that there is a direct connection between the confidence interval and the p-value. If the confidence interval includes a risk ratio of 1, then the p-value will not be statistically significant. Basically, the confidence interval says that the risk ratio might be 1, and the non-significant p-value says that the true risk ratio might be 1. Conversely, if the confidence interval excludes a risk ratio of 1, then the p-value will be statistically significant. Basically, the confidence interval says that the risk ratio is not 1, and the significant p-value says that the true risk ratio is not 1. For the first study, the confidence interval includes 1, and so the p-value is not statistically significant. For the second study, the confidence interval includes 1, and so the p-value is not statistically significant. For the third study, the confidence interval excludes 1, and so this time the p-value is statistically significant. But finally, for the fourth study, the confidence interval includes 1, and therefore, again, the p-value is not statistically significant. So, regardless of whether we want to use confidence intervals or p-values, only 1 out of the 4 studies allows us to conclude that the higher dose was more effective than the standard dose. To this point, we've been looking at each study in isolation. One of the things that we can do with a meta-analysis is to synthesize the results of the 4 studies. This will yield an analysis based on some 28,000 patients rather than the more limited number of patients in any single study. Concretely, we can compute a weighted mean of the risk ratio in the 4 studies. When we compute the weighted mean, we get a risk ratio of 0.85. This tells us that, on average, for the populations in these 4 studies, being assigned to a high dose rather than a standard dose reduced the risk of a cardiovascular event by 15%. This risk ratio is also bounded by a confidence interval that goes from 0.79 to 0.92.
The confidence interval is displayed here as a diamond, but the endpoints of the diamond have the same meaning as the line that we use for the individual studies.
The confidence interval here serves the same function as the confidence interval for each study. For example, in the PROVE-IT study, we sampled 4,600 patients from a population.
The risk ratio in that sample is 0.84, but the risk ratio in that population could fall anywhere from 0.68 to 1.04.
The same idea applies to the summary effect in the meta-analysis. In this analysis, we sampled 4 populations from a universe of similar populations. The mean risk ratio in this sample of 4 populations is 0.85, but the risk ratio in the universe of similar populations could fall anywhere from 0.79 to 0.92. So, to recap, in each study, we're using a sample to generalize to one population, and in the meta-analysis, we're using these 4 populations to generalize to all similar populations. The confidence interval for the mean excludes 1, and so we conclude that in the universe of similar populations, the higher dose is more effective than the standard dose.
Or, working with the p-value is less than 0.001. And so we conclude, again, that the higher dose is more effective than the standard dose.
By contrast, when we were working with the individual studies, 3 out of the 4 studies yielded results that were not statistically significant. That's because each study was based on a relatively small amount of data, while the meta-analysis was based on substantially more data. Each study included data from 4,000 to 10,000 patients, while the meta-analysis included data from some 28,000 patients. And while 4,000 patients might seem like a large sample size, the precision of these analyses and the statistical power depends on the number of events in each study, not only on the number of patients. And even in a sample of 4,000 patients, the number of events was relatively small. 3 of the 4 studies were not able to show that the higher dose was better, but the meta-analysis was able to show this. So that's one of the things that we're going to do with a meta-analysis. By synthesizing data from all the studies, we're able to get a more precise estimate of the mean effect size than we could from any single study. Something else that we can do with the meta-analysis is to look at the pattern of risk ratios. So far, we've established that the high dose is more effective than the standard dose on average. But what does the pattern of results look like? Is it the case that the risk ratio is reasonably consistent from study to study? In that case, we might conclude that we should use the high dose for all populations. Or is it the case that the risk ratio varies substantially from study to study, such that the advantage of the high dose over the standard dose is very strong in some studies, but only trivial in others? In that case, we might conclude that we need to know where the high dose is superior and where it is not. Looking at the data, I would say that the impact here is consistent. The risk ratios in the samples all fall within a narrow range, from around 0.80 to 0.90. And we'll spend time later showing how we can quantify this. For now, I wanted to point out that we should be looking at the pattern of effects as well as the mean effect, and that the meta-analysis allows us to do so.
Now that we know where we're going, let's return to the start and actually run the analysis.
To recap, this is the Cannon analysis that compared a high dose of statins versus a standard dose of statins. Each study is a randomized controlled trial where patients were randomized to either treatment. The researchers kept track of the number of patients in each group who suffered a cardiovascular event. I'm going to use the program Comprehensive Meta-Analysis, or CMA, which is the program that we developed. However, you'd be doing something similar if you used any other program and you'd get the same results. First, let's have a look at the data. In practice, you normally type the data directly into CMA. But for purposes of this workshop, I've put the data into Excel because this will allow me to show you the data before we start. Also, I'll be able to copy the data from Excel into CMA to save some time. So I have 5 columns of data. The first column holds the study names. Columns B and C hold the number of events and the sample size for the high-dose group. Columns D and E hold the number of events and the sample size for the standard dose group. The column labels are in row 1. Let's have a look at the first study in row 2. The study name is Prove It. There are 2,099 patients in the high-dose group, and of these, 147 had a cardiovascular event. There are 2,063 patients in the standard dose group, and of these, 172 had a cardiovascular event. That's all I'll need for the analysis, since CMA will compute the risk ratio automatically. However, I'm going to compute the risk ratio here as a part of this tutorial. I'll create a column over here called high dose risk. I'll create a column over here called standard dose risk. And then I'll create a column over here called risk ratio. For the high dose, the risk will be equal to 147 over 2099, which is 0.07. For the standard dose, the risk will be equal to 172 over 2063, which is 0.083. And then the risk ratio is the first risk divided by the second. This will be equal to 0.07 divided by 0.083, which is 0.84. And if you recall, that's the risk ratio we saw in the analysis. I can copy these formulas to the next 3 rows, and the results look like this.
The risk ratios for the next studies are 0.86, 0.80, and 0.89, which are the same numbers that we saw earlier.
As I said, this was simply to show where the numbers come from. We don't need them, so I'll erase them. Now let's have a look at CMA. To start CMA, I'll click the icon on my desktop. The program opens, and it looks like a spreadsheet. There's a tutorial that I can toggle on or off using the Help menu. I'll turn it off for now. The first thing I need to do is to insert a column to hold the study names. So I click Insert, Column 4, Study Names. The program inserts the column and labels it Study Names. The next thing I need to do is to insert columns to hold the summary data for the studies. One of the nice things about CMA is that it allows you to enter data for studies in many different formats. For example, if the studies report the number of events and sample size in each group, you can enter that. If the studies report the mean and standard deviation in each group, you can enter that, and so on. And you can mix and match so that you can enter a different kind of data for different studies. So the first thing we need to do is to tell the program what kind of data we want to enter. Then the program will create the columns that we need for that kind of data. In our case, we want to enter the number of events and sample size in each group. I click Insert, Column 4, Effect Size Data. The program displays this wizard, which I can use to select the format for my studies. On this screen, I can elect to choose from common formats or from all 100 plus formats. I'll choose all 100 formats. Then I click Next. On this screen, I can choose from 4 options. The first option says Comparison of 2 groups. This is the option that we will use in almost all cases. We'll explore the other options later, but for now, I'll simply choose the top option and click Next. When I want to compare the outcome in 2 groups, there are 5 basic types of data that I might be using. The first one is to compare the number of events in the 2 groups. The second is to compare the means in the 2 groups, and so on. I'll choose the first option, which is labeled Dichotomous Number of Events. When I click on that, the program displays 4 books, corresponding to 4 types of data. The first is for studies that compared 2 independent groups. The second is for studies that used matched groups or a pre-post design, and so on. In our case, patients were randomly assigned to either a standard dose or a high dose, so the 2 groups are independent of each other. And I'll choose the first book. For studies that looked at the number of events in each group and that compared independent groups, there are a number of formats for entering the data. The first is to enter the number of events and sample size in each group. This is our format, so I click on that, and the Finish button lights up. I click on that, and the program inserts the columns that I need. For Group A, we have the number of events and sample size. For Group B, we have the number of events and sample size. I have the option to label these columns. Group A is the high dose group, so I'm going to call this high. Group B is the standard dose group, so I'm going to call this standard. I can also label the events. For example, if the event was death, I might label the outcomes dead and alive. In our example, the event could be death or a stroke, so I'm simply going to leave the label as event or non-event. I click OK, and these labels are applied to the columns. For the high dose group, I have events and total sample size. For the standard dose group, I have events and total sample size. Notice that the screen is divided into 2 parts. The columns at the left are white, and these are the columns where I will enter the data. The columns at the right are yellow, and these are the columns where the program will display the effect size. When we enter the events and sample size for each study, there are several indices that we can use to display the effect size. One of them is the risk ratio, another is the odds ratio, another is the risk difference, and there are other options as well. By default, the program will display the odds ratio for each study. We can see that over here, where the program displays a set of columns for the odds ratio. In our case, we want to use the risk ratio, so we need to customize the display. To customize any part of the screen, I can right-click on that part. So I'll right-click on the yellow columns, and the program displays this menu. The last item on the list is the option to customize the computed effect size display. I click on that, and the program opens this dialog box. At the top, you'll see that the primary index is the odds ratio, and the indices that have been selected are the odds ratio and the log odds ratio. We'll discuss these later. For now, I want to put a check mark next to the risk ratio, and I want to put a check mark next to the log risk ratio. At the top, where I could select the primary index, I'll select the risk ratio. This is simply the index that the program will use by default for this file. Now I'll remove the check mark for the odds ratio and the log odds ratio. Down at the bottom, there are checkboxes for also show the standard error and also show the variance. I'll put a check mark next to each of these. Finally, we have the option to show the primary index only or to show all the selected indices. I'll choose show all the selected indices. To recap, the primary index is the risk ratio. I have a check mark for risk ratio and log risk ratio. I have a check mark for also show the standard error and for also show the variance. And I've selected the option to show all selected indices. At this point, I'll click OK, and the program makes the changes. We're now displaying the risk ratio, which is what we wanted. And now I can go ahead and enter the data for the 4 studies. I'll start by typing in the data directly. For the first study, the name is Prove It. In the high dose group, we have 147 events out of 2,099 patients. In the standard dose group, we have 172 events out of 2,063 patients. As soon as I type that in, the program shows the risk ratio is 0.84. Of course, this is the same number that we saw before when we looked at the results and also in Excel. The program also displays these as log values. The program will work with log values in the computations, but this is all done behind the scenes and you never need to look at these. The values are displayed for those who find them useful. Now I'll enter data for the second study. The study name is A to Z. In the high dose group, we have 205 events out of 2,265 patients. In the standard dose group, we have 235 events out of 2,233 patients. As soon as I type that in, the program shows that the risk ratio is 0.86. I could type in the data for the next 2 studies, but to save some time, I'll copy it from Excel. I switch to Excel. In Excel, I'll select these 2 studies. I'll press Ctrl-C to copy the data. I'll return to CMA. I'll click in row 3 in the first column. I'll press Ctrl-V to paste the data. The program fills the cells and shows the computed effect sizes. The risk ratios for the 4 studies are 0.84, 0.86, 0.80, and 0.89. At this point, I can save the file. I click File, Save As, and give it a name. And then I click OK. Now I'm ready to run the analysis. I click Run Analysis on the menu bar. And here the program displays the names of the studies. Here the program displays the statistics for each study. And here the program displays the plot of all the studies. We can set the scale for the plot. To do that, as always, we right-click on the plot. And since we're working with a ratio, the options are 0.5 to 2, 0.1 to 10, and 0.01 to 100. We'll select 0.5 to 2 because this captures the range that we need for the set of studies. Now, this should look similar to the plot that I started with. Down at the bottom of the screen, we can select the statistical model for the analysis. The options here are fixed effect, random effects, or both. I'll select random effects. And here, the program indicates that this is the model being used. Later, we'll discuss why this is the correct model. In this particular example, the two models will actually yield the same results, but it's a good idea to get into the habit of selecting the correct model. At this point, we can look at the results. The effect size index is the risk ratio. The mean risk ratio is 0.849 or 0.85. The risk of having an event in the high dose group is 85% as high as the risk of having an event in the standard dose group. Or we could say that the high dose reduces the risk by 15% as compared with the standard dose. The studies in this analysis are based on 4 populations, and we assume that these populations are representative of a much larger set of similar populations. We want to generalize from these 4 populations to all similar populations. For example, all populations with similar cholesterol levels, general health, and age. In that larger universe of populations, we would estimate that the risk ratio was 0.85, but that's only an estimate. The confidence interval tells us how precise that estimate is. Here, the confidence interval is 0.79 to 0.92. In this universe of similar populations, the mean risk ratio probably falls somewhere in the range of 0.79 to 0.92. Or, the mean effect of using the high dose rather than the standard dose is to reduce the risk of an event by at least 8% and possibly by as much as 21%. We can also test the null hypothesis that the 2 doses are equally effective, or that in the universe of similar populations, the mean risk ratio is 1.0. The 95% confidence interval does not include 1, so we can reject the null hypothesis and conclude that the high dose is more effective than the standard dose. Or we can look at the test statistic and the p-value. The z-value for a test of the null hypothesis is minus 4.16, and the corresponding p-value is less than 0.001. So the test is statistically significant. We reject the null hypothesis and conclude that the high dose is more effective than the standard dose. The next thing we want to do is to estimate the extent of dispersion in effect size across the studies. If we simply look at the plot, it would appear that the risk ratios vary from around 0.80 to 0.89. However, we need to remember that we're looking at the observed effects, and we care about the true effects. That is, we're looking at the effect size in 4 samples, but we care about the effect size in 4 populations. It turns out that the dispersion that we see in the samples tends to be greater than the dispersion in the underlying populations. To understand why this is, consider what would happen if all 4 studies were based on the same population in the same hospital at the same time. Let's assume that the risk ratio for this population is actually 0.85. If the true risk ratio in this population is 0.85, then any sample drawn from this population will report a risk ratio that differs from 0.85 because of sampling error. Some will fall below 0.85 and some will fall above 0.85. Indeed, if all 4 of these studies reported a risk ratio of exactly 0.85, we would suspect that someone had manipulated the numbers. So, in a case where the true effect is identical for all studies, we expect to see a certain amount of dispersion in the observed effects. With that in mind, when we look at the observed effects in our 4 studies, we take the following approach. We compute the amount of dispersion in the observed effects, but then we subtract from that the amount of dispersion that we would expect to see based on sampling error alone. The difference gives us the dispersion in true effects. To see the numbers, I can click here on Next Table, and we see this table. The table is divided into 2 parts. The part at the left deals with the mean effect size, and the part on the right deals with variation in effect size. First, let's look at the left. The numbers here are the same as the ones we saw a moment ago on the prior screen. This line gives us the results for a random effects analysis, and so these are the ones that we'll use. The mean effect size is a risk ratio of 0.85. The confidence interval is 0.79 to 0.92. In the universe of similar populations, the mean risk ratio probably falls somewhere in this range. We can test the null hypothesis that the mean effect size in this universe is 1 and that the two doses are equally effective. The z-value is minus 4.16 and the p-value is less than 0.001. We reject the null hypothesis and conclude that the high dose is more effective than the standard dose. All of this deals with the mean effect size. Now we turn to the dispersion in effect size. Over here we have Q, degrees of freedom, and a p-value. Q is the sum of squares of all effects from the mean effect on a standardized scale. Degrees of freedom is the degrees of freedom for computing Q, and it's simply the number of studies minus 1. If all studies are based on the same population, and all the variance in observed effects is due entirely to sampling error, then the value of Q that we would expect to see is equal to the degrees of freedom. So the Q value that we expect to see based on sampling error alone is 3. The Q value that we actually see is 1.2. So the dispersion that we're seeing in the observed effects is actually less than we would expect to see based on sampling error alone. The next statistic here is the p-value. The null hypothesis being tested here is that there is no variation in true effect sizes. In other words, if we actually knew the true effect size in all similar studies, it would turn out that these effect sizes are all the same. If Q is greater than the degrees of freedom, we would use this p-value to test this null. A significant p-value would provide evidence that the effect size varies from study to study. But when Q is less than the degrees of freedom, as it is here, there's no evidence that the true effect size varies at all, and so there's no need to even look at the p-value. The next statistic is I-square. People think that this tells us how much the effects vary. This is wrong, and we'll talk about that later. But whenever Q is less than the degrees of freedom, I-square will be 0, as it is here. The next statistic is tau squared. Tau squared is the variance of true effects. Whenever Q is less than the degrees of freedom, tau squared will be 0, as it is here. And finally, we have tau. Tau is the standard deviation of true effects, and whenever Q is less than the degrees of freedom, tau will be 0, as it is here. So the one key statistic here is tau, which is 0. I'll click on Next Table to return to the main screen. The mean effect size is a risk ratio of 0.85. But to understand the potential impact of the treatment, we need to know if the impact is consistent or if it varies. I deliberately chose this analysis to start because it's relatively simple in that Q is less than the degrees of freedom, and therefore the standard deviation of true effects is estimated as 0. The fact that the standard deviation of effects is estimated as 0 tells us that the effect size is consistent across studies. Let's run through an example of how I might report these results in a publication. I'll start with a brief introduction, then I'll have a section that deals with the mean effect, and another section that deals with the heterogeneity in effects. So we're talking here about Canon high dose versus a standard dose of statins. First, a summary. The analysis included 4 studies, each of which compared patients who were randomly assigned to either a standard dose or a high dose of statins. The outcome was mortality or cardiovascular event, and the effect size was the risk ratio. First, I'm going to deal with the mean effect size. Is statin dose related to the risk of a cardiovascular event? The mean risk ratio was 0.849, which means that being assigned to a high dose rather than a standard dose of statins resulted in a 15% lower risk of an event. These studies were sampled from a universe of possible studies defined by certain inclusion-exclusion rules as outlined in the full paper. The confidence interval for the risk ratio is 0.786 to 0.917, which tells us that the mean risk ratio in the universe of similar studies could fall anywhere in this range. the range does not include a risk ratio of 1, which tells us that the mean risk ratio is probably not 1. Similarly, the z-value for testing the null hypothesis, that the mean risk ratio is 1, is minus 4.164, with the corresponding p-value of less than 0.001. We can reject the null hypothesis that the risk of an event is the same in both groups and conclude that the risk is lower in the high dose group. So that deals with the mean. Next, I deal with heterogeneity in effect size. How much does the effect size vary across studies? The observed effect size varies somewhat from study to study, but a certain amount of variation is expected due to sampling error. We need to determine if the observed variation falls within the range that can be attributed to sampling error, in which case there's no evidence of variation in true effects, or if it exceeds that range. The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 1.242 with 3 degrees of freedom. Thus, the observed dispersion is actually less than we would expect to see by chance. It follows that there's no evidence that the true effect size varies from study to study. The I-square statistic tells us what proportion of the observed variance reflects differences in true effect size rather than sampling error. Since the variance in true effect sizes is estimated as 0, I-square must be 0. Tau square is the variance of true effect sizes in log units. Here, tau square is 0. And finally, tau is the standard deviation of true effect sizes in log units, and here, tau is 0. So that's the basic analysis. Next, I might want to create a high-resolution plot to include with the report or to show in PowerPoint. I click High-Resolution Plot. The plot might retain some settings from an earlier analysis, so I'll click Reset All. Under Color Mode, I'll select Colors for Slides. And now my screen looks like this.
The next thing we can do is to set the dimensions of the plot. I click File, Page Size. Let's assume that we want to send this slide to PowerPoint. Until recently, PowerPoint used a ratio of 4:3, and now it uses a ratio of 16:9. If you're working with CMA version 4, you can select either option. If you're working with CMA version 3, the only option is PowerPoint, and that corresponds to the older version of PowerPoint. So if I want to use the newer version, I'll select PowerPoint and then make some changes. I set the dimensions to 1600 by 900. I'll leave the left and right margins at 50, and I'll change the top and bottom margins to 40. I click OK, and now the plot displays the new dimensions.
The basic idea of the high-resolution plot is pretty simple. There are two main ideas to keep in mind. First, the plot that we see here will be based on the main analysis screen. If I want to modify what columns are being displayed here, I would return to the main analysis screen, make those changes, and then return back here. Second, once we tell the program what columns we want to display, those columns will expand to fill all available space. So if I want the text to be larger, I cannot assign a larger font to the text. Rather, I would remove some columns so the remaining columns will expand and take up the additional space. Initially, I have columns here that display the same statistics I saw on the main screen. Then, here I have the forest plot. And the forest plot also has a space immediately to its left and immediately to its right. This space serves to provide a buffer between the plot and the other columns. The space to the right of the forest plot would be useful if I had data to the right. But in this example, there's no data to the right of the forest plot. So I want to remove this extra space since it is not needed. I right-click on the forest plot. I select the menu for spacing and forest plot width. There are tabs that allow me to adjust the space between the rows, to adjust the space between the columns, to adjust the width of the forest plot, to adjust the buffer to the left of the forest plot, and to adjust the buffer to the right of the forest plot. I click the tab to adjust the buffer on the right side of the forest plot. And there are a series of buttons over here. The ones in red will make the buffer smaller. The ones in blue will make the buffer larger. This one will reset the buffer to its original width. And this one will remove the buffer entirely. That's the one that I want. I click this button and notice what happens. The buffer is removed, and the rest of the plot increases in size to fill the available space. To see that again, I can click Reset, which will reset the buffer to its original width. Then I click Remove, and we have the larger text and the larger plot. I might decide that I want to remove the z-values from the plot. The z-value and the p-value provide information about the test of significance, but the p-value is really all that I need. If I remove the z-value, I'll have more room for the other columns. To remove the z-value, I need to return to the main analysis screen. I click Return to Table, and here I have all of the columns that report statistics. To modify the set of columns, I can right-click anywhere within the set. Then I click Customize Basic Statistics. And this is a list of all the basic statistics. I remove the check mark for the z-value, and I click OK. The z-value column is gone. I click High Resolution Plot. The z-value column is gone, and the remaining text is now larger. Now that I have more room to work with, I'd like to expand the width of the forest plot. I right-click on the forest plot. I click Spacing and Forest Plot Width. I click the tab for Forest Plot Width. The two buttons in red will reduce the width of the plot. The two buttons in blue will increase the width of the plot. In each case, two arrows means a large change, and one arrow means a small change. I'll use one arrow up to increase the width in small increments.
And I'll click that a few times.
The forest plot now looks like this, and the other columns have been modified to make room for the forest plot. At this point, my columns are set. For additional clarity, I can increase the space between the rows. I right-click on the statistics. I select the menu for spacing and forest plot width. I select row spacing. As always, I have a red arrow to decrease the spacing and blue arrows to increase the spacing. I'll use the button with one blue arrow to increase the spacing in small increments. I click this once, twice, and so on. Now I want to change the title. I right-click on the title. I change the text to High Dose versus Standard Dose Statins. I click Apply. The program makes the change and also adjusts the size of the plot to accommodate the title.
I can also change the font size for the title.
On the forest plot, the labels are Favors A and Favors B. I right-click on the labels. I change the labels to Favors High and Favors Standard. I know that this is Favors High and this is Favors Standard because I checked this before. If not, I would go back and check it now. I click Apply. I want to add a footer to the plot. On the menu, I select Format, Footer. I add the text, Random Effects Analysis, TAW equals 0. I click on the check mark, which tells the program to activate this footer. I click Apply. I want to change the font size for the footer. I click Font. I click the up arrow twice. And at this point, I might want to send this plot to PowerPoint. I can change any of the colors by clicking on Colors. For now, I'll leave them as is. I click File, Export to PowerPoint. The program opens a copy of PowerPoint and inserts this plot. Now suppose that I want to send a copy to Word. I return to CMA. I click in Color Mode and select Colors for Printing. I click File, Export to Word. And the program opens up a copy of Word and inserts a copy of the plot. Let's return to CMA. Again, I'll click Return to Table and return to the main analysis screen. Let me show you a few more things here. I said before that the summary effect size is a weighted mean of the individual effects. Some studies get more weight than others. To see the weights, I click the tool labeled Show Weights. I can see that 13% of the weight was assigned to the first study, 19% to the second study, 31% to the third study, and 37% to the last study. Now I'll click this button to hide the weights. If I revert to the high-resolution plot, these weights are reflected in the size of the box for each study, specifically the area of the box. For example, the weight assigned to the fourth study is 37%, and the weight assigned to the second study is 19%. So the fourth study gets approximately twice the weight of the second study. If you actually measure these boxes, you'll find that the area of this one is precisely twice the area of this one. The process of assigning weights is complicated, and we will discuss it at length later. But for now, we can use this simply as a kind of sensitivity analysis. That is, we see that every study has a non-trivial part in the summary effect, and no study dominates the analysis. For example, if it had turned out that 80% of the weight was carried by one study, I might be concerned that the results do not reflect the synthesis of 4 studies, but rather one study alone. In that case, I might be concerned about generalizing from these studies. But that turns out not to be a problem here, since no single study gets more than 37% of the weight. There are many other options that we can speak about, but I'll return to those in a later section. To recap, I've introduced a few concepts so far. One is the idea of an effect size. This is the index that captures the impact of the intervention. In this example, the effect size was a risk ratio, but there are others that we could use as well. And over the course of the day, we'll spend time talking about that. Another is the concept of weights. Some studies are assigned more weight than others, and we need to understand how we assign weight to a study. I mentioned the fact that we need to choose a statistical model. Typically, we choose between the fixed effect model and the random effects model. I said that the correct model in this case was the random effects model. We need to discuss what these models are and how to choose between them. I introduced the idea of heterogeneity. I said that in this case, the impact of the intervention is consistent across studies. We need to discuss how we quantify heterogeneity and how it affects the potential utility of the intervention. I mentioned that a meta-analysis is based on the effect size in each study rather than the p-value for each study. I want to spend some time discussing that. In the modules that follow, I'll spend some time discussing each of these issues, and for each, I'll use a few examples to ensure that the concepts are explained fully.